All right, time to do our second problem with free fall. So I have the first one over here. I'll post this as well. We're going to do a second problem, and this problem, the ball is thrown upwards at 15 meters per second. So even though this is thrown, anytime that it's in the air, from the second it leaves the hand, the whole time it's in the air, the only force on it is gravity, so it's still in free fall. Even though it's not falling, it's still in free fall. So we do this problem, it asks how high does it go? Okay, so what is its maximum height? And then how long does it take for it to return? So, again, can be kind of a tricky problem. We read this problem, and there's only one number that the problem actually gives us. We know that this ball is thrown up at 15 meters per second, but we're going to be able to figure out how high it goes and how long it's in the air total just from that initial velocity. So, just like over here, our steps are going to be to draw the problem. I kind of drew it out right here. It's good to label some different points, and I'll talk about that in a second. I could have drawn it a little bigger, but... So we draw the problem first. I'll talk about labeling that in a second. We write down any of our givens, and I usually write down the entire list. What am I doing? Change in x, t, v final, v initial, and a. So we're going to write down any problems, any givens the problem tells us, and anything we know. Okay? Right away, if it's a free fall problem, I'll write this one down first. Right away, if it's a free fall problem, we know the acceleration is negative because it's down 9.8 meters per second squared. The acceleration is always negative. Okay? It's always down. The Earth is always pulling these balls towards the ground, which means it's always changing its motion to be going more down. Even if it's still traveling upwards, it's slowing down because it's getting pulled down. Acceleration is always in the direction of the net force. We learned that last unit. So it's always getting pulled towards the ground. Even though it's not moving towards the ground, it's still accelerating down. So down is going to be negative here. So I'll write a little key over here where up is positive. It's good to write that down on your drawing so that you know anything that's pointing up is positive, any vector that's pointing down is negative. So we have our acceleration. A ball is thrown upwards at 15 meters per second. Now, one important part of all of these problems is determining where your initial and final points are. Your velocity at your final point is what VF means. Now, we can make our final point a whole bunch of different things. We can make it halfway up, we can make it at the top, we can make it at the very end. Where do we want to sort of end the stopwatch here, or end looking at our problem? Well, part A says how high does it go? What that means is we want to know how far it goes from here, that's our initial point. We don't want to know how far it goes all the way to here. Its displacement is 0 if that's our final point. So what we want to do is we want to kind of stop this video or stop looking at this motion up at the top. Okay, this is going to be our final point. That's a little trick to do some of these problems, is to cut the problem in half almost. If this marker's getting thrown up, we're only going to analyze the top half of that motion. We could also analyze the second half of the motion. They're mirror images. All right, the time for this thing to go to the top, and we're going to use this fact later on. These are just some extra notes, extra facts about if a ball's thrown up in the air. If something's thrown up, the first half of the motion is a mirror image of the second half, right? So the time it takes to get up there is the same as the time it takes to fall down. The speed right when it leaves my hand and the speed right when it comes back and hits my hand is the exact same, just in different directions. All right, so I probably should write this. V initial is the opposite direction, but the same number as V final. Right? They're mirror images of each other. At the top, and this is another reason we cut the problem in half, we actually know that the velocity at the top is 0. Even though it just stops for a brief second, it's never just like sitting there hovering. But when it's at the top, it's turning around. It's starting to turn around. The speed, it stops very momentarily, stops at the top. Okay? If I think about moving this way and then turning around to move this way, at some point I have to be traveling 0 meters per second. I'm going positive, positive, positive numbers, okay, and then I turn around to go negative velocities. At some point I have to cross 0. I have to be going 0 meters per second. So anyway, going up as it turns around at the top to come back down, at the very top, the velocity is 0 meters per second. All right? We're going to use that. If we put our final point up here, we actually know that the final velocity, since we are not worrying about the second half of this motion right now, the final velocity is 0 meters per second. Even though when it hits my hand on the way back down, it's not 0 meters per second. It's moving the same speed actually it was before. But we're just going to look at the first half of this problem because we want to know how far does it go from here up to the top. So this is what we're looking for. How high does it go? We're looking for how far the displacement from here to here. What was its change in position? Now, when we're talking about vertical motion, free fall, that's height. How far it went is how high it went. Those are the same, right? So if it's asking how high it goes, it's asking for the displacement. Part B is asking for the time as well. For part A, though, we won't worry about the time. Well, we know the initial velocity, too. The initial velocity it gives us in the problem is 15 meters per second. So once again, we have a problem where the problem only writes down one number. It only gives us one number, but we know 3 different things. So we do the same thing we did back here. The next step is to choose an equation with, and again, that motion study guide from CK12 has a list of like the 5 equations that we can pick from. We pick an equation that has exactly these 4 in it, but not time, because for part A, we don't know the time and we don't care about it. It doesn't ask for it. So we pick an equation with those 4 variables in it. It might take a little while. Another way to pick that is pick the equation without time in it. There's only one equation without time. Pick that one. That equation, if we look for it, is VF squared equals V initial squared plus 2 times A times change in X. Right? This is just got to make sure. One note on these, especially when something's traveling up and then down, careful about positives and negatives. Anything pointing up is positive, anything pointing down is negative. And again, the physics part of it is over. The kind of the thinking can be over now. It's just math from here on in. Just plug and chug. The physics is done. So V final is 0. We plug that in there. 0 squared equals 15 squared plus 2 times negative 9.8 times the thing we're looking for. We can either call that h because we're dealing with vertical problems, or we can keep it as change in x. How far did it go from here to here? All right, we can do some math here. 15 squared is 225. So 0 equals 225 minus 19.6 times change in x. We can't split these two up yet. We gotta subtract 225 from both sides. We get negative 225 equals negative 19.6 times change in x. Now we can undo this multiplication here. A lot of people will see this negative and try to add 19.6 to both sides, but that's not what is happening to the variable. The number negative 19.6 is being multiplied to change in x, so we have to undo that multiplication. So we divide both sides. Divide by negative 19.6. Divide by negative 19.6, both sides. Make sure the right number crosses out. And we get, divided by 19.6, 11.5. So 11, and it ends up being a positive number, which makes sense because it goes up 11.5, up 11.5 meters. And that should be how high it goes. It ends up 11.5 meters higher halfway, and then it comes back down. Now part B says, how long does it take to get for it to return? The way to do this one, there are two ways to do this one. One is, I think, a lot easier in the way I do it. You could treat this entire problem from start to finish. This is your initial point. Your final point, you use that it's the final velocity is negative 15 meters per second, and you try to pick an equation to find time. I find that a lot more difficult and a lot less useful. If you ever start and end at different heights, you can't really do this anymore. What I do is I split the problem in half and say, okay, the initial point's down here, final point's up here. We can keep the same givens. And then when we find the time, since it starts and ends at the same height, we can just double that afterwards. If it takes 2 seconds to get up to the top, then it'll take 2 seconds to fall, so the time in the air is 4 seconds. Be careful with what time they're asking for. If you maybe set up a problem and you find this is your initial point, this is your final point, oh, t equals 2 seconds, don't just circle it and move on to the next one, because it's not asking how long does it take to get to the top, it's asking how long it takes to get all the way to the top and all the way back down. So be careful to read the problem again and see what it's asking for. All right. So if you wanted to try this next part too, part B, how long does it take for it to return? Then this would be our question mark, our time. And we can really pick any equation with time, initial velocity, acceleration, final velocity, or change in x. Now what I like to do is I like to pick the equation with time, if it's a part A and a part B. I like to pick the equation that has these givens in it, all these 4 variables. 1, 2, 3, 4. Because just in case we got this one wrong, then we don't accidentally use that to find time. Doesn't really matter. We can pick any of them. For this one, we would pick basically the definition of acceleration. Acceleration is change in velocity divided by time. We can find time that way and then double it. All right. If you guys want to try that one, 15 over. The time it takes to return should be 3.06 seconds. So I'm not going to do that all out right now, mostly because I ran out of space and don't want to start over. But if you want to try that and check your work, it should take 3.06 seconds. That's another example problem you can do. All right, I hope that helps a little. I'm going to make another really quick video about some of the questions specifically in that CK12 assignment. I posted a new worksheet that you can do instead of the CK12 because it's really tricky, but I will make a couple of quick hints if you want to still try the one on CK12, even though it's really hard. All right.